At 6:23 p.m. on May 3, 1999, the portable Doppler on wheels radar unit recorded wind velocities that exceeded all documented atmospheric measurements in the continental United States. The instrument registered rotational speeds of 301 miles per hour plus or minus 20 miles per hour within the condensation funnel. This velocity represented a kinetic energy load 2.86 times greater than the maximum design threshold established by the American Society of Civil Engineers for residential construction in Tornado Alley. The mesocyclone traversed 38 miles of suburban terrain over 85 minutes. Its forward velocity averaged 27 miles per hour. This combination of extreme rotational force and extended exposure duration created a mechanical testing environment that no engineered structure in the affected municipalities had been designed to withstand. Residential construction protocols in Oklahoma during the late 1990s adhered to the International Residential Code standards with modifications specific to seismic Zone 1 classifications. Foundation systems consisted primarily of monolithic slab construction with embedded steel reinforcement mesh rated at 6 inches on center. Wall framing utilized dimensional lumber at 16-inch intervals, with hurricane clips rated for 90 miles per hour sustained wind loads. The building envelope incorporated asphalt composition shingles, mechanically fastened at manufacturer specifications. These specifications reflected probabilistic risk assessments that designated F3 classification tornadoes as the maximum credible event for the region. The enhanced Fujita scale methodology assigned F5 classification to wind speeds exceeding 200 miles per hour. Engineering models predicted that such velocities would generate differential pressure loads approaching 250 pounds per square foot on vertical surfaces. The anchorage systems in standard residential construction employed 5/8-inch diameter anchor bolts embedded 7 inches into concrete at 6-foot intervals along the sill plate perimeter. Laboratory testing had demonstrated that this configuration provided adequate resistance to uplift forces generated by design basis wind events. The factor of safety incorporated into these calculations assumed that extreme wind velocities would persist for durations measured in seconds rather than minutes. No residential structures in the Bridge Creek or Moore municipal boundaries had been engineered to withstand sustained exposure to velocities approaching 300 miles per hour. Atmospheric conditions on May 3, 1999, established a mesoscale convective system characterized by extreme thermodynamic instability. Surface temperatures reached 81 degrees Fahrenheit with dew points at 70 degrees Fahrenheit. This moisture profile generated convective available potential energy values exceeding 4,500 joules per kilogram. The 500 millibar wind field exhibited westerly flow at 70 knots, while surface winds originated from the south at 25 knots. This vertical wind shear created helicity values of 450 square meters per second squared. The Storm Prediction Center issued a high-risk convective outlook at 11:30 a.m. Central Daylight Time. Weather reconnaissance aircraft deployed drop zones that recorded a lifted index of -12. The cap suppression mechanism persisted until 3:47 p.m. when solar heating degraded the elevated mixed layer. Initial convective towers formed along the dry line boundary in Tillman County at 4:15 p.m. Satellite imagery documented explosive vertical development with cloud tops penetrating the tropopause at 55,000 feet within 23 minutes of initiation. The low-level mesocyclone signature appeared on WSR-88D radar at 4:47 p.m. Velocity couplets indicated rotation velocities of 45 meters per second at an altitude of 3 kilometers. The National Weather Service issued tornado warning number 478 for Canadian County at 5:29 p.m. Atmospheric soundings indicated that the environmental conditions would support tornadic activity for a minimum of 4 hours. Condensation funnel genesis occurred at 6:23 p.m. in Bridge Creek at coordinates 35.12 degrees north, 97.88 degrees west. The National Weather Service radar at Twin Lakes detected a tornadic vortex signature with a diameter of 0.8 kilometers. Initial damage surveys documented F2 intensity impacts on agricultural structures. The mesocyclone exhibited a northwest to southeast trajectory at an azimuth of 123 degrees. Ground reconnaissance teams observed a multiple vortex structure with satellite tornadoes rotating around the primary circulation. The Doppler on wheels unit positioned itself 2.3 kilometers south of the circulation center at 6:31 p.m. Spectral analysis of the returned radar signal indicated maximum wind velocities of 135 meters per second at an altitude of 20 meters above ground level. This measurement exceeded the previous documented maximum tornado wind speed by 27 meters per second. The condensation funnel width expanded to 1.6 kilometers as the system traversed into Newcastle. Photographic documentation captured a wedge configuration with multiple suction vortices evident along the debris cloud perimeter. The forward velocity decreased from 32 miles per hour to 21 miles per hour as the system intensified. National Weather Service meteorologist Doug Forsyth transmitted emergency bulletins describing the tornado as potentially the strongest ever recorded. The velocity measurements implied that residential structures would experience wind loads exceeding their ultimate capacity by factors of 2 to 3. The mesocyclone maintained F5 intensity for 38 continuous minutes while traversing residential areas. This duration represented an exposure time 15 to 20 times longer than typical extreme wind events. Structures experienced not only peak instantaneous loads, but cumulative fatigue effects as oscillating pressure differentials stressed connection points through repeated loading cycles. The vortex diameter of 1.6 kilometers meant that individual buildings remained within the high-velocity wind field for 2 to 4 minutes, depending on their position relative to the centerline track. Engineering analysis indicates that cyclic loading at frequencies of 2 to 5 Hz would induce resonance effects in wood frame structures. The combination of sustained uplift forces and lateral shear created a three-dimensional stress state that conventional anchorage systems had not been designed to resist. Structures located on the southeast flank of the circulation experienced the additive effects of the tornado rotational velocity and the forward translation speed. This vector addition increased effective wind speeds by an additional 27 miles per hour compared to structures on the northwest flank. The pressure differential between interior and exterior building spaces reached values approaching 7 pounds per square inch. Windows and doors failed early in the loading sequence, allowing pressure equalization but also removing structural diaphragm action from wall assemblies. The extended duration allowed wind-driven debris to progressively erode building envelopes through repeated impact loading. This cumulative damage mechanism reduced structural capacity throughout the exposure period. Forensic examination of foundation systems revealed a consistent failure mode: anchor bolts extracted from concrete slabs under pure tension loads that exceeded their rated capacity. The 5/8-inch diameter SAE Grade 5 bolts possessed an ultimate tensile strength of 120,000 pounds per square inch. At a stress area of 0.226 square inches, the theoretical failure load was 27,120 pounds. Field measurements indicated that uplift forces on typical single-family residences with 2,000 square foot footprints exceeded 500,000 pounds when subjected to 250 mile-per-hour wind velocities. With anchor bolts spaced at 6-foot intervals, the perimeter sill plate contained approximately 60 attachment points. This configuration provided a total system capacity of 1.6 million pounds under ideal conditions. However, the distributed load pattern and eccentricity effects reduced the effective capacity to approximately 40% of the theoretical maximum. Post-event investigation documented that 73% of destroyed structures had been displaced from their foundations as intact units. The structures translated distances ranging from 15 feet to 340 feet before disintegrating. High-speed video analysis indicated that once the sill plate separated from the foundation, the structure became aerodynamically unstable. The building envelope acted as a lifting surface, generating additional vertical forces. Tumbling rotation rates reached 2 to 3 revolutions per second. This rotational motion imposed centrifugal loads that exceeded the shear capacity of wall-to-floor connections, causing rapid structural disintegration. Subsurface utility infrastructure sustained damage modes not previously documented in tornado forensic studies. Natural gas distribution lines composed of polyethylene pipe with 3/4-inch diameter and 100 psi pressure rating experienced mechanical separation at service connections when structures displaced from foundations. The flexible pipe material typically accommodated ground movement through elastic deformation. However, the violent extraction of meter assemblies exceeded the material strain capacity. Field surveys identified 438 natural gas line ruptures in the Moore impact area. The released methane dispersed rapidly in the high-velocity wind field, preventing accumulation to explosive concentrations. However, scattered ignition sources, including severed electrical conductors and friction sparks, initiated 64 structure fires in the immediate aftermath. Fire suppression operations encountered complications when water distribution mains also sustained damage. The 8-inch diameter cast iron pipes installed in the 1960s fractured when soil movement exceeded the joint flexibility limits. 3 major water main breaks reduced system pressure below the minimum threshold for effective firefighting operations. Electric power distribution infrastructure experienced complete mechanical failure. Wooden utility poles snapped at ground level when bending moments exceeded the modulus of rupture for southern yellow pine. Aluminum conductor cables detached from support structures and became entangled with debris. The distribution network serving 12,000 residential customers sustained damage, requiring replacement of 89% of the components. Interstate 44 experienced traffic congestion as residents evacuated ahead of the confirmed tornado track. The roadway reached capacity, with traffic volumes exceeding 2,400 vehicles per hour per lane. Forward progress rates decreased to 8 miles per hour. Multiple vehicle accidents created blockages that further degraded throughput. Motorists abandoned the highway and sought shelter beneath overpass structures at 4 locations along the affected corridor. This decision placed approximately 150 individuals in environments that created Venturi effects. The confined geometry beneath bridge decks accelerated wind velocities by factors of 1.3 to 1.8 times the ambient flow. Pressure differentials in these constricted spaces reached extreme values. Post-event analysis indicated that debris transport velocities approached 180 miles per hour in the reduced cross-sections beneath overpasses. 13 individuals sustained serious injuries from debris impact and pressure-related trauma while sheltering in these locations. Highway traffic remained immobilized for 7 hours after tornado passage. Debris blocked all lanes for continuous distances exceeding 2 miles. Overturned vehicles and collapsed structures created obstacles that required heavy equipment removal. The Oklahoma Highway Patrol documented that Interstate 44 did not return to normal traffic flow for 23 hours. Emergency response vehicles attempting to access impact zones encountered delays averaging 45 minutes due to roadway obstruction. This mobility degradation occurred during the critical initial response period when rapid access determined survival outcomes for trapped victims. Terrain reconnaissance 12 hours after tornado passage revealed landscape modification that eliminated conventional navigation references. Residential streets became unidentifiable when all structures and vegetation disappeared. Survey teams utilized GPS coordinates and property records to determine locations within the impact zone. The complete removal of surface features extended across a damage path 1.6 kilometers wide and 38 kilometers long. This represented a total affected area of 60.8 square kilometers. Aerial photography documented that 100% of structures within the core damage path experienced destruction classified as F4 or F5. The debris field extended beyond the primary damage corridor, with scattered building components recovered at distances up to 12 kilometers from their origin points. Electric utility restoration operations required reconstruction of the entire distribution network. The complete destruction of pole-mounted transformers and service drops necessitated replacement of 2,847 individual components. Crews worked 16-hour shifts for 21 consecutive days to restore power to affected areas. Natural gas system restoration required pressure testing of 14.3 miles of distribution mains. Utility crews identified and repaired 438 service line failures. Water system repairs demanded excavation and replacement of 2.7 miles of fractured pipe. The simultaneous failure of all three utility networks created interdependencies that extended restoration timelines. Electric power was required to operate natural gas distribution control systems. Water pressure was required to safely restart natural gas service. The sequential restoration process extended basic service restoration to 38 days for the most severely impacted areas. The Doppler on wheels unit recorded maximum wind velocities of 301 miles per hour with an uncertainty margin of plus or minus 20 miles per hour. This measurement established the highest objectively measured tornado wind speed in meteorological records. The enhanced Fujita scale classification system assigns F5 intensity to wind speeds exceeding 200 miles per hour. The measured velocities exceeded this threshold by 101 miles per hour, or 50%. Damage survey teams from the National Weather Service documented 1,780 destroyed residential structures. An additional 2,584 structures sustained major damage requiring reconstruction. The Oklahoma Department of Emergency Management compiled economic loss estimates totaling $1.2 billion in 1999 currency values. Insurance claims processing identified that 78% of destroyed structures lacked adequate coverage for total loss scenarios. The storm produced 36 direct fatalities and 583 injuries requiring hospitalization. Casualty analysis indicated that 89% of fatalities occurred in residential structures that experienced complete destruction. The remaining fatalities occurred in vehicles or in individuals caught in open terrain. The injury patterns documented blunt force trauma from debris impact in 67% of cases. Pressure-related injuries, including pulmonary barotrauma, comprised 18%. The mortality rate of 2.0% relative to exposed population reflected the effectiveness of warning dissemination and the availability of below-ground shelter spaces in a subset of structures. The National Oceanic and Atmospheric Administration's Storm Prediction Center implemented enhanced Fujita scale operational use in February 2007. The modified scale incorporated improved damage indicators and degrees of damage to provide more accurate intensity estimates. Oklahoma amended state building codes in 2014 to mandate engineered anchorage systems for new residential construction in high wind zones. The specification required anchor bolt diameter increases to 3/4 inch, with maximum spacing reduced to 4 feet. The amendments also mandated continuous rod tie-down systems for roof-to-wall connections. These modifications increased residential construction costs by approximately 3%, but provided measurable improvements in wind resistance capacity during subsequent tornado events.